Hi, hello students, good evening everyone. I hope all are doing well. And welcome back all of you to Infinity Learn JEE channel by YouTube channel by Sri Chaitanya. This is me Surya, your chemistry faculty from Infinity Learn. I hope I'm perfectly audible and visible to each and everyone present over here to watch this particular session. If anyone is watching this particular live, just give me a hi in the comments so that I can identify whether I'm audible or not. Hi Dhananjit, good evening. Welcome to the session. Okay, in the last class we have discussed about the ideal and non-ideal solution, right? So here again we are just repeating the same topic with some questions here. So I hope you guys have covered to the topics that we have covered in the last class. Okay, what we have covered already about the ideal and non-ideal solution, right? So what do you mean by the Raoult's law? What is the explanation for the Raoult's law? So here again we need to just repeat or revise the same topic about the ideal and non-ideal solution. Right? What do you mean by ideal solutions? Hi, good evening. Yes, the solutions which obeys Raoult's law, right? Which obeys Raoult's law at the entire range of concentration or composition is known as the ideal solution. In terms of pressure, we can say that the total pressure is always equal to the pressure that expected from the Raoult's law, right? That is the case in the case of ideal solutions. If you are talking about the intermolecular force of attraction, what will be the force of attraction there in the case of ideal solutions? If any of the solution which is forming from the solute and solvent, right? What will be the intermolecular force of attraction between solute solvent molecules in the case of ideal solutions? It will be similar, right? That is given here. AA, that is the solute molecules. BB is the interaction between solvent molecules. And A and B is the interaction between the solute and solvent molecules in the case of solution, right? It is in the case of ideal solution. Then some of the examples are given here. You need to keep in mind about the examples. First one, it is benzene plus toluene solution. And again, it is hexane plus heptane solution. I hope it is clear. We have already discussed in the last class. Clear? Okay. Then if you are talking about the non-ideal solutions, what do you mean by that? In terms of Raoult's law, any of the solutions which does not obey at the all entire range of concentration are known as non-ideal solutions, right? Bhavna Kumari, what is your doubt? Do you want to repeat it again? Ideal solutions, ma'am. Okay, in the case of ideal solutions, just watch my particular previous session, which is recorded yesterday. Then I will just give an idea about the ideal solutions. Any of the solutions which always obeys the Raoult's law at the entire range of concentration is known as the ideal solutions. If you are talking about the intermolecular force of attraction, right? If you are taking a solute A and solvent B mixing together, we will get a solution of AB, right? So if you are saying that if there is the intermolecular force of attraction is similar, if the intermolecular force of attraction is similar, what will happen to the vapor pressure? It will be always same, right? In terms of solute, solvent and solution, it will be always same. So such type of solutions are commonly known as ideal solution. I hope it is clear now. If still it is not clear, just go through the previous session which is already recorded in the same channel. Right. So in case of non-ideal solutions, which means that there will be two types of deviation shown by the solutions. One is positive deviation and the another one is negative deviation. Right. What you are observing from the positive deviation? the vapor pressure is always higher than that expected from the Raoult's law is known as the positive deviation. Right? P of total is always greater than here. What you can expect from the intermolecular force of attraction there? If a solution is forming by using a solute A and solvent B, right? So if there is an intermolecular force of attraction between these, solute and solvent molecules are very weak. How it will observe if I am heating the solution, what will happen? These solute and solvent molecules can easily escape out, right? Which means that their vapor pressure is always higher. Clear? That's why they are showing positive deviation from the Raoult's law. Is that clear now? Then some of the examples are given here. Water plus ethanol molecule, ethanol solution, and another one chloroform plus CCl4 solution. Then what about the negative deviation? What about the negative deviation? It should have less vapor pressure as compared to the Raoult's law, right? Yes. As compared to Raoult's law, if you are talking about the intermolecular force of attraction there, in the case of these particular solution, what will happen to the solute interaction? In the case of solution, the solute and solvent interaction is very high, right? Very strong. So we cannot easily escape out the A and B molecules there in the solution AB. So which means that we need more heat, right? We need more heat, or vapor pressure is very low here as expected from the Raoult's law. Clear? Is that clear now? Again, example is very important. Water plus acetic acid and chloroform plus acetone molecule, right? Sorry, ether molecule. Yes. And then here is the representation of the graphical representation for the ideal solution. This is already discussed in the last class. This is the vapor pressure, which is given in the y-axis. This is the mole fraction given in the x-axis. So if you are talking first here, chi1, that is the mole fraction of the first component, that is equal to 1 here. Then obviously chi2 is equal to 0, right? So here chi1 is equal to 0 and chi2 is equal to 1. So if you are talking about the Raoult's law explanation here, you will get the value of pressure is equal to P10 at chi1 is equal to 1. Then pressure is equal to P20 at chi2 is equal to 1. This will be the representation of graphical representation of vapor pressure versus mole fraction for the ideal solutions. Similarly, you can draw the graphical representation for positive and negative deviation. This is the vapor pressure. This is the mole fraction. Right? Can you please give me the idea about whether it is showing positive or negative deviation? The first graph. Is it the graph for positive deviation from the Raoult's law or negative deviation for the Raoult's law? The first one. Okay, what will be the answer? If you are talking about the graph here, right, this is the expected, these dotted lines are the expected graph for the ideal solutions. But what you are observing here, in the first case, vapor pressure is higher than expected from the Raoult's law, right? Which means that it shows the graph for positive deviation, right? Clear? Yes. Then obviously the second graph is for the negative deviation, right? Negative deviation. The vapor pressure, yes, vapor pressure produced is always less than expected from the Raoult's law here in the case of second case, which means show the negative deviation from the Raoult's law. Clear? Is the thing clear? Just let me know in the comments. Yes, fine. Now let us practice some questions which is based on the ideal and non-ideal solutions. Here is the first question. Read the question carefully, then let me know the answer in the comments. The question is a solution of two miscible liquids showing negative deviation from Raoult's law. What will be their conditions in terms of vapor pressure and boiling point? Okay, this is the latest question in the JEE Main exam. Okay, Pranav, are you sure? Is it option B? Lost mode option A. Let's see. Is there any other options? Okay, just recall the idea about what we mean by the negative deviation. What will happen to the vapor pressure in the case of negative deviation? Then think about the boiling point and you will get the correct answer here. Okay, let's take the answer here. Option D is the correct answer, right? So, negative deviation from the Raoult's law. What will happen to the vapor pressure there? Negative deviation. Vapor pressure decreases or increases? Decreases, right? Vapor pressure decreases in the case of negative deviation. And obviously, what will happen to the boiling point? We need more heat to boil the particular solution, right? So, decrease the vapor pressure and increase the boiling point is the condition for the solution which is mixing with two miscible liquids having the negative deviation from the Raoult's law. Is that clear? Is that clear? Yes. Again, we can make one more question here, right? If you are talking about the positive deviation, what will be the condition here among these three options? If you are talking about the positive deviation instead of negative deviation here. Is my question is clear? Similarly, if you are taking the same solution, but it is showing the positive deviation from the Raoult's law, what will be the condition for here among these three options? Now it will be option B, right? Positive deviation means it will show more vapor pressure as compared to the previous one or the expected from the Raoult's law. So, as the vapor pressure increases, what will happen to the boiling point? Decreases, right? So, increase the vapor pressure and decrease the boiling point will be the condition for positive deviation from Raoult's law. Clear? Okay, here is the next question. Okay. Before that, there is a small topic I have forgot in the last class. It is about the azeotropes. What do you mean by azeotropes? Pranav, which point I want to repeat? Last case. Okay, I think it is about the positive deviation, right? Okay, if the question is changed by positive deviation here, what do you mean by positive deviation? Obviously, the vapor pressure is always higher than that expected from the Raoult's law, right? So, condition will be increased vapor pressure and boiling point will be decreases. We need less temperature to boil the particular solution, right? So, option B will be the correct answer for if the question was asking for the positive deviation. Is it clear now? Okay, fine. And let me move to the next topic, that is about the azeotropes. When you are talking about the Raoult's law, that is about the non-ideal solutions, we need to talk about one more type of solution, that is the azeotropes. These are the binary mixtures. Binary mixtures means which contain two components, right? So the binary mixtures that is having the same composition in liquid and vapor phase. Same composition in liquid and vapor phase, and it is boiled at a constant temperature. It is boiled at a constant temperature. That type of solutions are commonly known as azeotropes. Clear? Azeotropes. So, both the solutions are boiled at the same temperature. We cannot be easily separate these solutions by using fractional distillation, right? I hope you must have idea about the process of distillation, right? Here, the solutions of the components are separated by using the difference in the boiling point, right? So in the case of azeotropic mixtures, all the solutions having the same boiling point. So we cannot be easily separate these azeotropic mixtures by using the fractional distillation method. Clear? So again, in terms of azeotropic mixture, we need to talk about the two types of azeotropic mixtures. First is minimum boiling azeotropes. Minimum boiling azeotrope. Okay, what you are expecting there? Minimum boiling. In terms of boiling point, how we can explain the minimum boiling azeotrope? Minimum boiling azeotrope is with the mixtures in which boils at a temperature less than their normal boiling point, right? It boils at lower temperature. Then the same we can be explained by using the Raoult's law. The solutions which shows a large positive deviation. Large positive deviation means high vapor pressure, right? High vapor pressure, and obviously very low boiling point, which means it becomes a minimum boiling azeotrope. Is the thing clear? Yes. Then what about the maximum boiling point? Boiling azeotrope. It will boil at a temperature higher than the normal boiling point, right? Boils at high temperature. So if you are thinking about the Raoult's law here, right? Raoult's law means here we can explain these according to Raoult's law as the solutions which shows large negative deviation. Negative deviation means low vapor pressure. Vapor pressure decreases as that of boiling point increases. So it will boil at a very high temperature as expected from the normal boiling point. So this is a maximum boiling azeotrope. An example is given here, nitric acid plus water. Clear? And it is the example which is given in the NCERT textbook. In the examination point of view, I mean the JEE Main memory based questions, many of the time this topic is repeated. We need to identify the examples of azeotropic mixtures. Some of the examples are given, you need to identify whether it is minimum boiling azeotrope or maximum boiling azeotrope. So this will be very important. I hope it is clear. Now let us practice the another question. Identify the mixture that shows positive deviations from Raoult's law. Positive deviation from Raoult's law. Yesterday when I was taking about the ideal solutions and non-ideal solutions, I have already given some of the examples which is given in the NCERT textbook. And this is the question which is based on the pure NCERT. What will be the answer? The first example is given acetone plus aniline mixture. And the second one chloroform plus acetone. Third one chloroform plus benzene mixture. The last one acetone plus carbon disulfide. What will be the answer? Positive deviation. Yes, again option D is the correct answer, right? Pranav, you are correct, very good. So option D will be the correct answer here. Just refer the NCERT textbook which is already given in the NCERT textbook. Right? That's all about the ideal and non-ideal solutions. We have already discussed about the Raoult's law, positive deviation we have seen, negative deviation seen, and about the examples it is very important. Now let me move to the next important topic from the solutions chapter, that is about the colligative properties. What do you mean by colligative properties? Let's see how we can define these colligative properties. So many of the solutions show some properties, right? So such as properties that depends only on the number of particles. That depends only on the number of particles of the solute, not about their identity, not about their nature. That particular properties are known as colligative properties. Clear? So whenever if someone is asking about you about the colligative properties, we can just define these properties as the properties of the solutions that depends only on the number of particles of the solute. Number of particles of the solute, not about their identity or nature, right? So here in this particular topic, we need to focus about the 4 types of colligative property. The first one is relative lowering of vapor pressure. Relative lowering of vapor pressure of solution, right? Relative lowering of vapor pressure of solution. Then elevation in boiling point of the solution. Third one, depression in freezing point of the solution. And the last one, osmotic pressure of the solution, right? These are the 4 different colligative properties we need to focus in our based on our examination point of view, right? So here we need to focus the first property here, that is the relative lowering of vapor pressure. So if you are talking about the colligative property, what is the application of this colligative property? We can easily identify the amount of solute, right? Amount of solute by using the, we need to find out the molecular weight of the non-volatile solute by using these 4 different colligative properties. Let us see some problems also. So let us talk about the first property here. That is a relative lowering of vapor pressure. Relative lowering of vapor pressure. As the name itself suggests, there will be the lowering of vapor pressure, right? Lowering of vapor pressure. So if you are taking a solution, if you are adding a non-volatile solute there, obviously their vapor pressure decreases, right? Vapor pressure decreases. That term is introduced as the relative lowering of vapor pressure, right? So there is a small derivation to calculate the relative lowering of vapor pressure. I need your complete attention here. So we can just say that if you are talking about the vapor pressure of a solution, right? Vapor pressure of a solution. In terms of solvent, we can say that this vapor pressure is always less than that of the pure solvent. Less than that of the pure solvent. So if you are talking about the Raoult's law here, how we can apply here? This P1 is the vapor pressure of solution and P10 is the vapor pressure of pure solvent. right? So here we are applying the Raoult's law. As we already know, P1, vapor pressure of solution is equal to the vapor pressure of pure solvent into mole fraction, that is chi1, right? This is the first equation given here. Now if you are taking the change in pressure there, change in vapor pressure there, how we can take that? We already know that the vapor pressure of solvent is always less than the solution, right? So we are taking delta P, change in pressure, is equal to P10, the vapor pressure of pure solvent minus vapor pressure of solution, right? So P10 minus P1. Then what I am doing here, we know that P1 is equal to P10 into chi1, right? P1 is equal to P10 into chi1. So here, instead of this P1, I am taking this equation here. What I am getting here, P10 minus P10 into chi1. Is the thing clear till now? Right? So P10 minus P10 into chi1. Now I am taking P10 from outside. So what we are observing here, P10 into 1 minus chi1. P10 into 1 minus chi1. Clear? Is there any doubt? Right? So delta P is equal to P10 minus into 1 minus chi1. As we already know, if you are talking about the mole fractions, the sum of mole fractions should be equal to 1, right? Chi1 plus chi2 is equal to 1. So if you are taking here, I can say that 1 minus chi1 is equal to chi2, right? 1 minus chi1 is equal to chi2. So I am just writing here like this, delta P is equal to P10 into chi2, where chi2 is the mole fraction of the solute. Is that clear? So delta P is equal to P10 into chi2. If you am taking the value here, delta P divided by P10 is equal to chi2, right? Delta P divided by P10 is equal to chi2. Just rearranging this equation and you will get the answer, delta P divided by P10 is equal to chi2. Then the first equation, as we already know, P1 is equal to P10 into chi1, right? So I am taking here P10 minus P1 divided by P10. Yes, P10 minus P1 divided by P10 is equal to chi2. This left hand side term is known as the relative lowering of vapor pressure. Is that clear, everyone? Just applying the Raoult's law here, rearranging, you will get the answer is around P10 minus P1 divided by P10, where P10 is the vapor pressure of pure solvent, P1 is the vapor pressure of solution. Again divided by P10, that is equal to chi2. Chi2 means the mole fraction of the solute. Mole fraction of the solute. As we already know how to calculate the mole fraction, right? If you are talking about the solute, in terms of solute, we can say that number of moles of solute divided by number of moles of solute plus number of moles of solvent is equal to the mole fraction, right? So we can say that the relative lowering of vapor pressure, the relative lowering of vapor pressure of solvent is equal to the mole fraction of the solute. Is that clear? Is that clear? Just let me know in the comments. Yes. Okay, fine. So, if you are talking about the dilute solutions, dilute solution means what will be the number of moles of solute as compared to the solvent, it should be very, very less, right? Number of moles of solute is always less than that of the solvent in terms of dilute solutions only. As dilute solutions only, right? So we can just rearrange the equation as number of moles of solute divided by number of moles of solvent. Is the thing clear? Hi Jaitrick, good afternoon. Right? So number of moles of solute divided by number of moles of solvent. If you are talking in terms of molecular mass and given mass, right? So W of solute divided by M of solute. From that we can identify the number of moles of solute, right? Similarly, we can find out the number of moles of solvent by using W of solvent divided by mass of solvent, right? If you are taking the difference here, if you are taking the answer here, you will get the answer is around W2 into M1 divided by M2 into W1, where M1 and W1 are the, this is the molar mass, this is the given mass for the solute. 1 stands for solute here and 2 stands for the, 1 stands for solution here, 2 stands for the solute here. Clear? So, as we are talking about the relative lowering of vapor pressure, what you are observing here, it depends only on the molecular mass, right? It depends only on the amount of particles, right? Amount of particles. So we can define this relative lowering of vapor pressure as a colligative property. Is that clear? Is that clear? How we are deriving the relative lowering of vapor pressure? How we can calculate the molecular weight of solute by using the relative lowering of vapor pressure? How it is connected to the mole fraction? Then we can say that it depends only on the solute concentration, not about their identity or the nature. So we can call this as a colligative property. Clear? Okay, fine. So that's about the first colligative property here. Based on that, we need to practice some more questions. Okay, here is the first question. Read the question carefully. Okay, again, we need to find out the relative lowering of vapor pressure of a solution containing 1 mole of urea in 54 gram of water. This is the urea solution. Solute is urea and solvent is the water. You need to find out the relative lowering of vapor pressure. What will be the answer? There is a simple calculations only. Option 1. Is there any other options? Class 11, option 2. Are you sure? Let us see the answer here. Option 4, that is 1 by 4 is the correct answer here. How we can solve this question? Relative lowering of vapor pressure is connected with the mole fraction of the solute, right? Mole fraction of solute. What is the solute given here? It is urea, right? Urea. So, okay, what is the number of moles of water here? The given mass is 54 gram, right? Okay, given mass is 54 gram. What is the molecular mass of water? Molecular mass of water, H2O. 16 plus 2, 18, right? So 54 divided by 18, that is equal to 3. So number of moles of water is here 3 moles. And it's already given here the number of moles of urea is equal to 1 mole, right? Number of moles of urea is equal to 1 mole. So if you are taking the mole fraction here, it is equal to 1 divided by 1 plus 3, right? The simple calculation, that is equal to 1 by 4. Is the thing clear now? Okay, colligative property, right? So any of the properties of the solutions that depends only on the number of particles of the solute, not about their nature. If you are using any of the solute particles, these properties are depends only on their concentration, right? Such properties are known as colligative properties. So here we need to focus on the four different types of colligative properties. The first one, it is the relative lowering of vapor pressure. The second one is elevation in boiling point. Third one, it is depression in freezing point of the solution. The last one, it is osmotic pressure of the solution. So here we are focusing only about the relative lowering of vapor pressure. So what do you mean by relative lowering of vapor pressure? Okay, there is a small derivation. I am not repeating again. Just go through that. So after derivation, you will get the relative lowering of vapor pressure. That is P10 minus P1 divided by P10, where P10 is the vapor pressure of the pure solvent and P1 is the vapor pressure of the solution. The relative lowering of vapor pressure of the solution is equal to the mole fraction of the solute, right? Mole fraction of the solute. So if you are talking about the dilute solutions, we can define the relative lowering of vapor pressure as W2 into M1 divided by M2 into W1, where W1, W2 are the given masses for the solute and solvent respectively. M1 and M2 are the molecular masses for the solute and solvent respectively, right? So if you are talking about this expression here, we can say that this particular property, that is this particular property of relative lowering of vapor pressure, depends only on the solute concentration, right? So we can call this property as a colligative property. Is that clear now? Class 11. Hi Lakshmi Bansal. Arev, hi. Okay, is that clear now? Yes, okay, fine. So here is the next question based on the first colligative property. Solve the question, just let me know the answer in the comments. There is no any particular options, so just do the calculations. The question is mass of urea required to be dissolved in 1000 gram of water to reduce the vapor pressure of water by 25% is gram, nearest integer, and it is given that molar mass of nitrogen, carbon, oxygen, hydrogen are given as 14, 12, 16 and 1 respectively. Here it is again urea solution, NH2CO NH2. Okay, what will be the answer for this question, or how we can solve this question? Okay, what is the data given here? Here given the weight of water, right? Water is a solvent here, so we can take it as W1. This is already given 1000 gram, right? 1000 gram. Then, what is another given data? The vapor pressure is reducing up to 25%. 25%. Yes. Class 11. Yes, you are correct. This is the answer, right? Okay, great. So, the weight of water is given 1000 gram. And what is given here? It is relative lowering of vapor pressure is 25%. If I am converting it in the 25%, it will be relative lowering of vapor pressure 25%, or I can be written it as 1 by 4, right? Is there any doubt? 1 by 4, right? So, as according to our equation, relative lowering of vapor pressure is equal to the number of moles of solute, right? Okay, what will be the answer given here? If you are solving, what will be the answer for N2 here? Okay, you will get a decimal point here by solving this equation N2. You can just multiply the value of N2 into the 60 gram per mole. But 60 gram per mole is the molecular weight of urea. Then you will get the answer is around 111 gram. Sorry. Yes. Right? Okay, what will be the answer for N2 here? Just let me know. N2. Are you sure? 18.52? Okay. It is 18.52. If you are multiplying with the 60, it will be around this answer, right? So just do the calculations like this. The main point you have to be keep in mind that the relative lowering of vapor pressure is always connected with the mole fraction. So you need to identify the solute given here, mole fraction of the solute, by using the number of moles of solute divided by number of moles of solution. Then you will get the correct answer here. Clear? Okay, here is the next question. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram when added to 39 gram of the benzene. What will be the vapor pressure of the solution? If it is 0.845 bar, what is the molar mass of the substance? The first case, the vapor pressure is given as 0.850 bar. If you are adding 0.5 gram of solute to the 39 gram of the benzene solvent, you will get the vapor pressure is around 0.845 bar. You need to find out the molar mass of the solid substance. Okay, what will be the answer for this question? Okay, vapor pressure of pure benzene, right? That is the P10, our pure solvent. It is given 0.850 bar, right? 0.850 bar. If you are adding a particular amount of solute, right? For example, I am taking W1 here. That is our solute weight. That is equal to 0.5 gram, right? 0.5 gram. Which is added to the solvent. That is equal to W2. W2 is equal to 39 gram, right? 39 gram. What will happen to the vapor pressure? It decreases to 0.845 bar, right? So P1 is equal to 0.845 bar. Now apply the relative lowering of vapor pressure equation here. That is P10 minus P1 divided by P10. (0.850) divided minus 0.845 divided by 0.850. That is equal to M1, that is the molecular weight of the water, right? Sorry, benzene. What is the molecular weight of benzene? C6H6. It's already given, it is 78, right? 78 divided by M2, we need to calculate. M2 into W1. W1 is given here, it is 0.5 gram, right? So if you are solving, you will get the answer is around 169.03 something. It can be converted up to nearest integer, that is 170 gram. Clear? Is that clear? Just apply the mole fraction here in terms of relative lowering of vapor pressure, which is already given in the data. While solving here, you need to get the value of M2 here as 169.03 something. and it can be converted up to the nearest integer as 170 gram. Clear? Okay, is that clear? Just let me know. Okay, here is the last question. It feels like a little bit lengthy. A set of solutions is prepared using 180 gram of water as a solvent and 10 gram of different non-volatile solutes A, B and C. The relative lowering of vapor pressure in the presence of these solutes are in the order. It is given that molar mass of A is given as 100 gram per mole and B is given as 200 gram per mole and C is given as 10,000 gram per mole. The question is, a solution is made up of 180 gram of water here. By adding a solute of A, first solution, if you are adding the second solute of B, it will become the next solution. And third solution prepared by mixing 180 gram of water with the another solute C, right? So 3 different solutions are given here. You need to identify the order of relative lowering of vapor pressure for the 3 different solutions. 3 different solutions. Okay, how we can approach this question? Relative lowering of vapor pressure, right? It is connected to the mole fractions of chi A, chi B and chi C, right? These are the non-volatile solute adding to the particular solvent here. And the solvent is given as 180 gram of water, right? So first step we need to find out the number of moles of water. How it is? How much it is? 180 divided by 80. Ten moles, right? J-Trick, I am from NIT, not from IIT. Right, so we got the number of moles of water here. First we need to find out the number of moles of A, right? Number of moles of A. In all the solutions, 10 gram of solute is added, right? 10 gram of solute. So we are taking 10 by molar mass of A is 100, right? 10 by 100. So 10 by 100 divided by 10, right? That is equal to 1 by 100 here. Then what about chi B? Number of moles of B. Again 10 gram of B is adding to the solution having the molecular weight of 200, right? 10 by 200. That will be the number of moles of B here. So 10 by 200 divided by 10, right? Then what about the last one, chi C? Number of moles of C. 10 divided by 10,000, right? So what will be the order? We have already seen about the relative lowering of vapor pressure, right? So here, the relative lowering of vapor pressure is very less for the solute C, right? So the order will be A greater than B greater than C. Clear? Okay, is that clear? Option, I mean, A greater than B greater than C will be the correct order for the relative lowering of vapor pressure for this particular 3 different solutions. I hope it is clear. What you have to do, you need to find out the number of moles, then find out the mole fraction. So as we already know, the relative lowering of vapor pressure is connected with the number of moles of solute divided by number of moles of solution or the mole fraction. So just find out the answers here, then you will get the correct order. Clear? Okay, that's all about from my side for today. So far we have discussed about the ideal and non-ideal solutions. We have seen about the positive and negative deviations from the Raoult's law, and then we have practiced some questions based on the particular topic, and we have discussed about the colligative properties, right? Any of the properties that depends on the number of molecules of the solute, not on their identity, that properties are known as colligative properties. Here we have discussed about the first colligative property, that is a relative lowering of vapor pressure. In the next class, I will be coming by with the other 3 colligative properties, that is elevation in boiling point, depression in freezing point, and the osmotic pressure. We need to focus on some of the numerical problems based on that also. Again, there is a gentle reminder about the AITS, that is for the JEE Advanced exam. Infinity Learn is providing the JEE Advanced test series here, so enroll fast. Then there is another opportunity about the college predictor. If you have the idea about your JEE Main scores, you can just take the link from the description, then put your JEE Main scores here. You will get an idea about the colleges that you are getting according to your JEE Main exam scores, about the NITs, IITs and so on. So just enter your score fast in this link given in the description. Then if you are not getting any good ranks in the JEE Main exam, no need to worry. There is more other exams like private engineering exams. So again, Infinity Learn is providing you the test series for that particular private engineering exams. You will get a 70% off by using the best 70 off code. So don't miss this opportunity. Okay, I hope you guys have enjoyed the session. If you really like the session, hit the like button, share this particular session to your friends and family. Subscribe our channel, Infinity Learn JEE YouTube channel. Then, if you have any doubt, you can ask. Otherwise, we can wind up the session for today. No, right? So we can just wind up the session for today. Thank you so much, all of you. Bye-bye and take care.